All right, we're going to go ahead and get started. Is everyone awake and excited? Yes. Because I like to talk to you about something I'm so passionate about, and that's signal integrity and testing. So my name is Ebrahim Abunasrah, and I work for a company called Multilane, Inc. And I want to talk to you today about SCD21, Skew, Crosstalk, and the effects on bit error rate during the cable assembly manufacturing process. So we all know that the pace of network development means time to market is measured in days and weeks and not months and years anymore. Doubling the data rate comes with substantial testing. And what that means for end users is test time increases. That means manufacturing challenges that need to be addressed. It means everything needs to happen at the blink of an eye. And bit error rate remains the golden standard to determine the effectiveness of new technologies. So when we think about all these other signal parameters, insertion loss, crosstalk, skew, they all have some kind of impact on bit error rate. But at the end of the day, bit error rate is what the end customers really like to think about. And at 224, it's really critical for us to understand what is causing the noise, what is causing the bit error rate to go high. And when we think about cable assembly manufacturing, a lot of this noise comes from skew, common mode conversion, crosstalk, return loss, impedance, TDR, and there's others. So a lot of these come not necessarily from the design or for the board itself, but a lot of them actually come from the cable assembly manufacturing process. And that's why it's so important to make sure that these issues are caught at the manufacturing and they're not going to end customer. Because the end customer, once it gets there, we all know that's hundreds and thousands of dollars worth of losses. And really, production-focused testing solutions, they need to be addressed. Oftentimes, customers or cable assemblers, they develop these products, and at the very last, they think about testing solutions. So as a forum, we all need to think about how to do that in the very beginning. So as I mentioned earlier, I work with a company named Multilane, Inc. These are some of our products. We sell BERTs, TDRs, we do S parameters, we have sampling oscilloscopes, and things like that. When we think about the interconnect evolution challenges, there's three things that I think about. One of them is the form factor evolution. Back years ago, in the 10 gig SFP days, it was so easy. 2 pairs, you plug it into a switch, that's it. No need to do any of that testing. But now we're seeing so many proliferations in terms of number of pairs, in terms of splitting of cables, and everything's becoming denser and denser. When we think about earlier before, it was DACs and AOCs, but now these interconnects have turned into very complex interconnects. So, ACCs, AECs, flyover, backplane, transceivers, these are all things that have proliferated over the last 5 years or so. And then even when we go a step further, thinking about configurations. When we think about a simple SFP plus 10 gig 2-pair cable that was very popular in the old days, now we think of all these splitter cables. You might have a QDD on one end and an 8 SFP on the other. You might have a backplane box. You might have a flyover. You might have a flyover to an OSFP. You might have a QSFP to 4 SFP-DD. So there's all these different configurations that we think about, and they all need to be addressed at the cable production testing perspective. And when we think about production testers, there's a use case behind this. In terms of specifically in terms of signal integrity, the use case is when we think about how a test looks like, it has a monitor typically, it's got test equipment. Let's see if this laser works. It's got test cables, RF switches, RF switch cables, might have a module compliance board, and it's got battery backup. Now, this is a very low-cost way to approach things, but there's problems with that, right? When you bend these cables here, what happens? Signal integrity gets affected. When you're trying to calibrate, what happens? Well, this is 4 cables with 8 switches, so this is 32 pairs, but imagine you have a 96 or 128 pairs of cables. That's a lot of calibrating to do. Switches. What happens if these switches goes out, especially when you're in high production volume manufacturing environment? You have to stop the production line, and your technicians have to go out and they have to troubleshoot the issue. That means you have 40 or 50 people who are on the production line. You have to stop the production line. That's time and money wasted. Changeover time. We talked about proliferations earlier. When you want to go from an QSFP DD to an OSFP, excuse me, there's changeover time behind this. You have to remove all these cables and you have to re-put them on. There's a lot of challenges when it comes to this use case. And even when we think about any of these bending or kinking too much, or an operator actually hit them too hard, what happens? The signal integrity gets worse. So any single thing that happens, you have to stop the line, stop the operators, you have to keep paying them for doing nothing, and you have to figure out what the problem is. Now, one of the good things about this, it's very accurate data, and it's the ability to test all S parameters. And the last disadvantage I'll talk to is unable to test crosstalk. Why is crosstalk important? We'll talk about that a little bit later. But if you want to try to do all this calibration, it's very hard to understand how to test crosstalk accurately. So when we think about SCD21, we think of, it's an S parameter. It's basically a measure of the common mode imbalance between a positive and a negative lane. So if you have a lot of skew in your pair, you're going to have a lot of the common mode energy, differential to common mode energy being lost because there's too much skew in the system. And what can cause this? And I'll show you another slide that talks about what causes this. What causes this? Well, your drain wire can be biased to the right side. That's going to cause skew and common mode conversion issues. Your drain wires can be misaligned. That's going to cause SCD21 and skew issues. Your insulation foaming could be different. That's going to cause SCD21 or skew issues. But really, to really get to the bottom of the talk, we want to understand how big of issues are these. The second parameter is crosstalk. So when you're sending, let's say, 8 differential channels going this way, and you have 8 coming back this way, they start talking to each other. And that causes crosstalk issues. So if you have a receiver over here and it's got all these pairs talking to it over here, it's listening to all the noise, that's going to cause some issues with your bit error rate. So it's really important that we understand what crosstalk is and what its effect is on bit error rate. And here's another example that we have here. So if you have a TX1 to RX1 going in this direction, and a TX2 going to RX2 going in this direction, there's going to be some leak over from here to here. That's your near-end crosstalk. And then transversely on the other side, we have TX1 coming to RX1 here, TX2 to RX2. There's going to be some crosstalk leaking over here. That's your far-end crosstalk. So we want to understand what causes a lot of this crosstalk. And there's a variety of factors. But one factor could be your PCB and your cable termination. So if you have a foil right here, and you strip the foil, and you have some insulation here, and your conductor is long here, you're going to get crosstalk that's leaking from top to bottom. That's just one example of an easy way that crosstalk can come and affect your line. So when we at Multilane think about when we're developing our solutions, we want to think about the use case, what's important, what's not important. And so we were curious. We wanted to do some testing. So what we have here is one of our boxes, our 4079 ELN, which is great for PCIe Gen 6 and 7. And we added some crosstalk into a cable assembly. And what we found is the more you increase your crosstalk, the higher the bit error rate goes. And it's pretty significant. It's not, going from e to the 12 to e to the minus 11 and stopping. No, it gets pretty high. So we think that crosstalk is a major effect on bit error rate. So we did a little bit more research on this, and we took 2 cable assemblies. One cable assembly, the foil was stripped very long. And when I mean long, I mean maybe 1.5 to 2 millimeters. So it's less than your fingernail, okay? And then we took another cable assembly that was stripped, let's just say like 0.5 millimeter. And what we saw is that we saw a major effect on bit error rate. So this is your integrated crosstalk noise on your x-axis. This is your bit error rate on the y-axis. So we can see when you put in 16 millivolts or less of noise or crosstalk, which is this cable here, then everything is fine. Your bit error rate is okay. But when the cable starts to get stripped too long and the crosstalk becomes higher, then the bit error rate starts to go much higher. So that's scary. That means if you were to build a cable assembly and it passes insertion loss and you didn't test crosstalk, what's going to happen? You're going to plug it into the system and it's going to fail. So when hyperscalers are out in the field and they have this cable that has failed bit error rate and they have to call the technician and their servers are down, that costs thousands and millions of dollars. So this is why it's really important for us to understand what is crosstalk, what is common mode conversion, what is skew, and what is their effect on the bit error rate. Conversely, we took a cable that had some high skew, and we looked at the bit error rate. And you can see here, it doesn't really seem to be an effect on bit error rate. You can see here the skew is fairly high on this pair, but the bit error rate is still fairly low. You can see here these two, the skew is a little bit low, but they have much higher bit rates. And even here, we have this one here that has low skew but high bit error rate. So we don't think skew looks to be a major fact of BER. Now that being said, there needs to be more investigation because there's several different types of skew. So when we think about skew, we think about TDT skew. The same thing here, we took a cable that has high common mode conversion, one that has less common mode conversion, and we looked at the bit error rate. So you can see here the yellow and purple, they're similar, but the BER is much different from them. And conversely, you can see the blue pair has one of the highest SCD21s, but it has the best bit error rate. Now, when we as a company design products and solutions, we think about how can we make this easier for the customer. So this is one of the solutions that we came out with. It's called the 1RU box. So instead of having all of these boxes in these big form factors, we're making them much less, much smaller, easier to test crosstalk, easier to test skew, easier to test insertion loss. There are these tests available in the market. This is an example of one that we have that tests your bit error rate, insertion loss, crosstalk, TDR, and it does it in a matter of seconds. So forcing your cable assembler to do crosstalk testing is a very important thing that should come out of this meeting. We also we talked about at the beginning of this proliferation and configurations and how those things changed. So there are vendors out there that have high lane count bit error rates. So if you think about, this is one of our bit error rate testers, and this is what we would call is a backplane box. And if you don't know what a backplane box is, it's just basically like a box with a bunch of backplane cables in it. We have a solution that can test bit error rate, crosstalk, insertion loss, TDR, and this is a drawer that plugs in there. So this comes out of one of the proliferations that we kind of studied in the market. Same thing here. We have an S parameter / crosstalk analyzer testing crosstalk in seconds. The same thing. This box can be turned into something like this and can test all of these in high volume production, including crosstalk, which, as we mentioned, is so important. And then we also have a TDR box that does the same. You can put multiple of these boxes together and put a backplane connector on there. So there are solutions out there that can test crosstalk in a matter of seconds that are good for production. So in conclusion, bit error rate is a very important part of DACs, AECs, backplane testing, boxes, and we think crosstalk has a very high impact on bit error rate, more than SCD21 or Skew. So if you're an end user and you want to make sure your cables are good, my bet would be to test insertion loss, TDR, and crosstalk. And we feel that crosstalk should be measured in a high volume manufacturing process. And as I mentioned, there are high throughput solutions out there for crosstalk measurements, and these are very essential. So this is the last slide. It's a call to action. The problem to solve is minimizing SI problems during cable manufacture. We need to understand more of what's important to test. Do we need to test various forms of crosstalk, various forms of skew? Do we need to keep looking in these different measurements? And we also need to look at the data rate impacts, 56 versus 112 versus 224. And we should come up with the crosstalk specification for high volume cable manufacturing. And this is my email address, and the call to action is, timeline is within 6 months. Any questions? I think we have maybe 1 minute. Okay, thank you very much.